talk, where we discuss how secure are blockchain systems. My name is Ashna Beg, and I will be your host. Let me give you a brief idea about what this talk is going to be about. Blockchain has been the talk of the town recently due to its decentralized and distributed nature. And this very nature also gives rise to potential threats to its security. In this talk, we will explore questions surrounding the security of blockchain technology. As a distributed peer to peer system that relies in its operation on the behavior of peers, multiple security threats are outlined due to various fundamental realities. Our guest speaker for today is Professor Dr. David Mohaisen, a professor at the University of Central Florida, the United States of America, and the director of the Security and Analytics Lab at UCF. His research interests fall in the broad areas of network systems and their security, adversarial machine learning, Internet of Things security, AI security, and blockchain security. And his work has been published in more than 150 research papers in leading ACM and IEEE conferences and journals. He is a senior member of ACM and IEEE. Now, without further ado, I would like to ask Professor Dr. David Mohaisen to begin with the talk.
Thank you. Thank you, everyone. Let me just go ahead and share my slides. Um, the talk is going to be a slight modification of title-wise, but everything is going to be the same as promised on the ACM website. So the talk today is going to be looking into a measurement-based understanding of blockchain system security. And so those are two slides that I was asked by ACM to include in my talk, a brief introduction of what ACM is and what it's about, mission-wise and vision. And I'm actually a proud ACM member. And clearly, you know what is the ACM Distinguished Speakers Program, but more formal information about that and other speakers and what they have to deliver is available at speakers.acm.org. So my talk today is going to be mostly on the security of blockchain systems. And you might be asking, why should we care about blockchain systems? Blockchain systems, and aside from the hype that's shared with the term, has the potential to be utilized in a range of applications, from the mitigations of DDoS attacks by improving authenticity, verifying software quality, or being used for storing an authentic form of keys, biometric keys, preventing hacks, adding some integrity to the public key infrastructure, hardware provenance, among others. And we foresee that addressing the security of blockchain as a technology would help improve trust in those applications if they are realized. In the rest of this talk, I would be talking a lot about Bitcoin in particular. And the one thing I want to make clear beforehand is that we do not really see in Bitcoin anything particular. We do not really care about the money value of Bitcoin as it fluctuates over time, or the significance of the application beyond what it presents to us as a distributed system, as a widely deployed test bed with the properties that we would benefit from in understanding of blockchains in reality, including their network distribution, latency, churn, users and their behavior associated with incentive and scale. And so we hope that the scientific outcomes from the Bitcoin analysis would guide us to understand the blockchains as a whole. And so before I get into the specifics of my talk, I want to highlight the general theme of research that led to this work. So our work started in 2017-18 with some early work on cryptocurrency analytics, looking into price predictions. And so we had some work that looks into understanding the utilization of network artifacts into predicting the price of Bitcoin and other cryptocurrencies. We looked also into translational research, where we took existing applications that would require some form of strict integrity, and we found how to utilize blockchain systems into guaranteeing those properties. And finally, I guess the larger part of our work has been focused on the blockchain systems attack surface. And so we have looked into two types of attack surface elements. We looked into application-specific attacks, and this includes what you perceive at the client side. And so we had realizations of memory attacks for DDoS attacks. We looked also into understanding the cryptojacking, that is utilization of resources on a victim machine for crypto mining. And finally, for the network layer attacks, we looked into partitioning attacks in general, and this is going to be the topic of today's talk. Earlier work in 2019, and followed by the two pieces I'm going to be focusing on of HashSplit and SyncAttack. So the rest of this talk is going to be outlined as follows. So first, I will provide an introduction, high-level introduction for those who are not working in blockchain systems. Then the partitioning attacks, SyncAttack, and open redirections. And so for those who do not know much about blockchain systems, at the center of blockchain systems, there is a thing called a ledger. And the ledger is a data structure that contains transactions. As you can see, like here, the ledger is a bunch of structures, firm structures that include transactions with other metadata. And the transactions are contained in blocks, clearly, and the blocks are going to be, in a way, chained or connected to one another, linked to one another through a hash function. And this is a cryptographic hash function. Given that it is a one-way cryptographic hash function, then the ledgers would be append-only and tamper-proof in the sense that if you are to change anything in the past, you have to reverse the hash function, thus violating the property of the one-wayness. And so that is for the ledger. What is the application? The application of blockchain system is a decentralized and distributed system that uses the blockchain data structure to record an event that is a transaction exchange. So let's talk about that in specifics, perhaps. And so the application would be perhaps a peer-to-peer network where nodes can share that ledger that we described earlier. And the transactions in that case are going to be a change of state in the network that would begin with the case where you have a consistent database state, then execution of the transaction where the state is not consistent, and then end of transaction where it is again consistent. And so for the consistency, there are a number of consensus protocols that are utilized, and cryptocurrencies are one such application. And so if you talk about Bitcoin in particular, for the Bitcoin, the peer-to-peer network is going to be sharing the Bitcoin blockchain ledger. And the transaction is going to be a record of money transfer. And as you can see here, there is an address and amount of money that is being sent, and then some transaction, like no transaction, total received, or final balance, and associated data. And the consensus protocol in this case is a protocol that ensures the consistency in among different peers holding the ledger. And so in the case of Bitcoin, it's a proof of work where you solve a mathematical challenge, called mining. And the challenge is, given the value L, you find R, an output of a hash function, such that the prefix of the hash function, of the output of hash function, is all zeros, up to D bits. This is very difficult to solve because you can envision that you have to hash repeatedly to reach that value, T, so that the first D bits of them are zeros. But it's very easy to verify. Given the input, the previous value, and the current output, you hash it, get the output, and then verify that the first bits are zeros. Solving the puzzle is also known as the Bitcoin mining process. A little bit more about the anatomy of blockchains. So the overlay peer-to-peer network builds on a physical network, that is the internet that we know and love. And that network has two types of nodes, full nodes and lightweight nodes. And the full nodes would include the full ledger. The lightweight nodes will include the header of the ledger, only the top part of the transactions, of the blocks. And moreover, nodes in the Bitcoin network are either reachable or unreachable nodes. And the distinction between them is quite important for what we will describe later. But for now, you can envision that the reachable nodes are nodes that contribute to incoming and outgoing connections in the network. So they contribute to the connectivity of the network, while the unreachable nodes contribute only to the outgoing connections, but not incoming connections, meaning that they do not contribute to the connectivity of others. And per one of our earlier studies last year, we found that there are about 12,000 reachable nodes and about 200,000 unreachable nodes. Okay, so I promise this is going to be the final slide before I get into the core of the matter with our analysis. And so oftentimes, attacks on blockchain systems would be for an application-specific goal. And generally speaking, the fundamental attack is, in this case, called violating blockchain consistency. But the goal of it is something that is very simpler. And let's go over what is meant by those attacks. And so let's say that you have a blockchain system. In this case, it's going to be 3 blocks that we have here with transactions, and you have a bunch of miners, those marked in black. Now let's introduce an adversary. And the adversary here has 51% hash power. And the adversary, what would do is that would mine on top of the current existing blockchain behind block 3. And so do the benign miners. And let's say that the adversary, given that the adversary has a 51% hash rate, will have a higher likelihood of producing the blocks before the benign users, who have 49% of the hash rate. And let's say that the benign users act in a benign way. So they would release the block as soon as it is realized, whereas the adversary hold the block back and only release it after the adversary has a k+1 number of blocks, larger number of blocks than that of the actual existing network. And so what happens is that, let's say that in the benign branch, there is a transaction that is buying X and giving it to the adversary, buying it and giving it to the user, excuse me, buying it and giving it to the user who owns that transaction. And let's say that, I apologize, got by my thought of line of thoughts by my kids talking in the background. So let's say that in the block that is produced by the benign miners, there is a transaction associated with a given merchant, and the merchant sees the transaction and commits to the product requested by the user. However, let's say that the malicious miners release the longer chain, and so the shorter chain is going to be canceled, and a transaction of the same origin in the new block is going to override the existing transaction that resulted in the purchase, and as such, double spending will happen. That is, the network is going to switch to the longer branch. The adversary will double spend the same money. And so a double spend attack is launched by replacing a public chain with a private chain, and it violates the blockchain consistency. So that is the background. Let's get into the details of our attacks. And so, by the way, these are 2 pieces of work. Actually, the entire work that I'm going to talk about today is basically done with one of my students who happened to be from Pakistan, Muhammad Saad. He joined me in 2018 from LUMS, Lahore University of Management Sciences, and he's now a research scientist at PayPal. All right, so again, these are like the first attack I'm going to present is going to be based on some measurements that we have done and presented in ICDCS 2019, and then a follow-up paper in ACM CCS 2021. And so as for the partitioning attack, based on some of our earlier studies, we have observed that Bitcoin overlay network is biasedly distributed in the physical network. And so we divide this kind of distribution bias into 2 types. There is spatial bias and temporal bias. And especially, you can, as we know, the internet consists of multiple networks. The autonomous unit of those networks is called AS, autonomous system. And what we found is that 24 of those ASs host about 50% of the nodes out there in the Bitcoin network. And this is very bad if you consider that there is tens of thousands of ASs. Moreover, three ISPs intercept 65% or 66% of the mining nodes. Let me see if we have any questions here. All right, so if you have any question, please just feel free to interrupt. My understanding is that this is going to be interactive session. If you have any question, please interrupt. So having 2/3 of the mining data being intercepted by three ISPs is really counterintuitive, particularly given the original premise of blockchain systems being vastly distributed. And so you can envision that someone who has control in a way or another over those 24 ASs or the three ISPs will be able to create a significant damage, adversarially to the blockchain network. The temporal partitioning is quite interesting kind of aspect of the network. And what we have found is that there is a weak network synchronization. And if you look at this figure, on the x-axis, there is snapshots of the network. On the y-axis, there is the number of nodes with a given number of blocks behind the current head of the block. And so you can find the green part is the number of nodes that are up to date with their view of the network. The orangish is one block behind, and then down to the brown is more than 10 blocks behind. And we can see that there are about 10% of the nodes that they have are more than 10 blocks behind. And you can basically feed those nodes like outdated or blocks that would result in double spending. Special temporal partitioning is where you can actually combine both. And so the novel insight that we had in this measurement is that there is a weak synchronization in the Bitcoin network, and this has not been incorporated in the past in analyzing blockchain in general. So we look into why this happens. And so what we found is that there are 4 different reasons. There's unreachable node, addressing protocol, a block relaying protocol, and a churn on the network synchronization. And we look into the contribution of each of those. So what we have found is that there is a significant level of churn in the network. On the x-axis here, we have sampling time, again, snapshots. And on the y-axis, we have the number of nodes, and the red line is going to be the cumulative, and the black line is going to be the current number of nodes at any point in time. And we have found that while the number of nodes at any point in time is roughly about 11,000 nodes, the cumulative grows significantly, which indicates that there is a significant change in the actual nodes that are present in the network. What we have found is that 8% of the nodes leave the network every day. And as a result, there is a decrease in the number of the out degree. That is, the out degree is somewhere around 10, but it fluctuates, like between all the way from 2 to 10. And in order to increase the degree, the nodes will have to connect to other nodes. But there's a weakness in the addressing protocol, and there's a large number of unreachable nodes addresses, as we have shown earlier. There is about 200,000 of them. And so as a result, you can imagine that a number of those is going to fail. And so only 11.2% of the outgoing connections succeed. And as a result of that, the network is still going to have a lower degree. And as such, there will be a weak synchronization. So this is the main insight. How do you utilize this for our attack? Let's start with an example. And so let's say that you have a bunch of nodes, M1 up to M4, and let's say that one of those nodes produces a block. Ideally, the block would be produced by M1, goes all the way from M1 to M2, 3, 4 instantaneously. Now, all miners receive the block at the same time, and no miners will gain a pre-mining advantage from the propagation speed in this case. Now, you see something interesting here. We have all nodes connected to one another. And that is a very idealistic scenario. You would not expect that to happen, particularly, as we know, the out degree of a node is bounded. 10 we saw in the previous measurements, even less. So let's say that, not every node is connected to one another. And let's see how things go. You have a block, the block gets created by M1, sent to M2, then from M2 goes to M4, goes to M3, and there is maybe a latency delay between nodes. And now here, miners will receive a block at different times. given that they are not, connected directly. And miners will start mining the block, the next block at different times. And we will see that there is a pre-mining advantage, and propagation speed varies between links, and so that will add to that pre-mining advantage. And so expect that M2 will start mining before M4, M4 will start mining between M3, and even if M3, let's say, is connected to M1 somehow, and the link between M1 and M3 is different from that of the sum of the link between M1, M2, M2, M3, M3, M4, you would anticipate also a difference in the mining advantage. All right, so these are two elements. Let's look at the third element where we have an adversary. Let's introduce an adversary. An adversary is going to be connected to everyone in the network, M1 through M4. And let's say that the adversary has a faster relaying speed. So a block comes from M1, goes to the adversary and to M2. Now the adversary, as soon as the adversary sees the block, the blue block coming from M1, it would block it, withhold it, and would propagate its own block to M3 and M4. As another block comes from M2 to M4, given that M4 already has a block that is equally good in its blockchain, then it will discard the benign block. And so this will create this partitioning, divergence of a view of the network. And so in this case, what we do is that we exploit the notion of asynchrony and violate the blockchain consistency with some small mining power. Let's see how that happens. So what are the attack objectives? The attack objectives or goals are to fork with concurrent mining on two branches of the public chain and violate the blockchain safety property. And so for the safety property, we use the common prefix property and the chain quality property. And the first entails that honest nodes have the last k blocks in common. And the second one, the chain equality, entails that the ratio of blocks contributed by the miners is going to be proportional to the miner's hash rate. And so there are a few challenges that we need to address before we can actually launch the attack in reality. And so first, detecting the mining nodes among the reachable nodes. And so we do that. Then we need to look into validating the non-uniform block propagation among the mining nodes. That is to say there is a mining advantage among nodes. And then construct the attack. And so for defining the mining non-mining nodes, we formulate the Bitcoin ideal world functionality. And that clearly categorizes mining and non-mining nodes and their roles, and specify the constructs of the lockstep synchronous network that preserve the safety property that we mentioned earlier. And this will be used as a blueprint for constructing the attack and its evaluation. Now, we look into the second assumption, which is the churn, which is the non-uniform propagation delay. And so we deployed crawlers to detect the mining nodes. We identified that there's about 360 of those nodes, and they have diverse hosting patterns, and this is something good, maybe. And then we look into how they actually exhibit different timing characteristics. So we verified the non-uniform block propagation pattern among the mining nodes by looking into that the nodes do not construct a complete connected topology, and as such, propagation will take different paths. Those paths have different weights of latency, and the overall latency is going to be differential. And this is not really our only finding. Other works have showed the same kind of conclusion. We also confirmed that conclusion from secondary datasets. All right, so how to launch the attack? First, you have the mining nodes, non-uniform propagation. You create a fork, and then you maintain the fork for k blocks. And then once the k blocks are maintained, you have two scenarios. If the fork persists for the k blocks, the common prefix is violated. If the winning chain has more blocks than the adversaries, then the adversary's hash rate, then the chain equality is violated, and as such, you violate the safety. We model a block race between the adversary and the honest miners, and the adversary is given, a chance that is 26% of the hash rate. And with a tweak, that is, the adversary is going to be connected to all the mining nodes. And other mining nodes will receive blocks at different times, and adversary will learn the time of the block reception for each node. And we model the block as a race outcome, where certain conditions of the outcome are going to be favoring for the adversary, while the others are going to be favoring of that of the benign users. And so the block that is shaded in red here, the top one, 8, 9 cases, are favoring the adversary, whereas the lower ones are going to be the case where the fork gets resolved, that is favoring the benign users. And so what we have found is that the common bricks property and the chain equality property can be violated with a probability that is greater than 0.5. Particularly, the first is violated with a probability of 0.72, and the second is with a probability of 0.83 for an adversary with a mining power of 26%. Countermeasures for this attack, well, you can envision simply that you can actually prevent an adversary from connecting to all nodes. So you can tweak the Bitcoin client to model the ideal port functionality, form a completely connected topology among the mining nodes. However, this is going to be problematic in the sense that you cannot really still propagate things at the same time, given the underlying network. Incorporate the application-specific countermeasures that allow the nodes to detect that there is an adversary and disconnect from this adversary. Imagine that you can actually allow every node to share its routing table. And so if you know like there is a common node in everyone's routing table, that is clearly the adversary, given the adversary is connecting to everyone. Conclusion, for this part of the talk, the real-world Bitcoin network is neither lockstep synchronous nor non-lockstep synchronous, and there is a non-uniform block propagation pattern. An adversary with a strong network reachability and selective block relaying capability will be able to repeatedly introduce forks. And we demonstrate its effect through HashSplit, and our work highlight gaps between theory and practice. Let me move quickly to the next part of this talk. And hopefully I will have plenty of time for questions. And so this is again a work done by my previous student, colleague now, Mohamed Saad, and is also published in ACM CCS in yet a different paper in the same year. And so this is again the violation idea of the blockchain consistency. So you start with a blockchain of sort and a bunch of miners. You introduce the adversary, and adversary has 51% of the hash power, and then the adversary is stealthily mining and only releasing blocks when the adversary has a k+1, thus invalidating existing blocks that are mined by benign users, and this would result in double spending. And so the double spend here always required some sort of mining capabilities, and we will look into this attack, how you can do that without mining capabilities. So the mining capabilities here, let's say that, well, the chances for the adversary to win the game is by basically persisting a fork for more than k blocks. And so you can imagine the adversary has a mining power of alpha, that is the mining power of the adversary, and the benign users, benign miners, have a mining power of beta. And the probability for the adversary to persist k blocks is going to be alpha over beta to the k. And so k is going to be the number of blocks that the adversary needs to persist. And so if you look in the original scheme, alpha was original scheme, original design of Bitcoin, that was 0.51. The adversary needs a majority, simple majority, to be able to persist k with a certain probability. And then there are some optimizations that happen in the past that look into improving that bound. The requirements for double spending can be reduced by optimizing alpha. This we have seen also in our previous work. By incorporating latency, we were able to introduce alpha to 0.26. The notable theoretical frameworks stipulated that violating the blockchain consistency requires some mining powers. And so it's always alpha over beta to the k. So we are mindful that there is a prerequisite to double spending attack is to fork. And we know that forks can also happen naturally if the block propagation delay having to incur to increase significantly, or the network out degree would fall below a threshold value through partitioning. So let's say that you have, again, M1 to M4, and if the delay, let's say that M1 produces a block, the block is sent to M2, M2, then M4, and let's say M3 has a block that is, an attacker's block. The block would be sent to M4, but given that M4 already has its own benign block, does not have any advantage over the block. The new block does not have any advantage over the block that M4 already has, and so it will be cancelled. But imagine that the adversary has control over the link between M2 and M4, so the block that is coming from M2 to M4 is not going to happen in the first place. So regardless, even if like M3 sends block M4 at any time, the network will not be seeing any visibility into M4. And so that is the idea that we utilize into this attack. So if the adversary completely controls the communication model, then arbitrarily can delay the block propagation among the miners and can create partitioning among the miners. So instead of competing with the honest miners, the adversary can make honest miners compete among themselves. And so instead of having alpha as the adversary's mining power, we can envision that alpha and beta both together have to be the benign honest users, honest miners mining powers, and the adversary will try to make them compete among each other, and then just play the game to the end and play with the winning faction. So adversary who can control that communication model can achieve that, and that is possible by exploiting the churn in the network. And so in the next few slides, I'll show you how that will happen. So recall from our earlier measurements about the root cause analysis that on average, there is about 12,000 IP addresses of reachable nodes found in the network in one day. And so if you look at the x-axis, we have the sampling time. On the y-axis, we have the number of nodes. And you can find, well, this is an updated view of the network. If you remember, mu in the previous slide was about 11,000. Here it's 12,000. It fluctuates over time, but on average, now we have about 12,500 nodes that are, or addresses that are persistent, that are reachable. On the other hand, we have a large number of cumulative, meaning that some of those come and some of those go. And how many of those go? There is a notable churn rate. On average, there is about 1,200 nodes that join the network and the same number that depart from the network at every day. So moreover, there is about 2,900 nodes that persistently stayed in the network for 60 days or so. And you can see, like, the number stabilizes. So that number is not significantly decreased after that period of time. So if an adversary occupies all the incoming connection slots of the existing reachable nodes, a newly arriving node cannot connect with the existing nodes. And so we will demonstrate that here with an example. Let's go over this example. Let's say that we have NR is the total number of nodes that are reachable. I is going to be the number of incoming connections per node, is going to be 3. OI is going to be the number of outgoing connections per node, is going to be 2. And RC is going to be total number of available connections is going to be 27. 3 by 9 number of nodes, 3 number of incoming connections is going to be 27. And RO is going to be 18. 18 is basically going to be the number of nodes by the outgoing connections. And RA is going to be the gap between RC and RO. That's going to be the available connections. That is to say, if every node has 2 incoming connections and 1 outgoing connection, then there's a gap of 1. It will allow 1 more incoming connection. All right. And then given that you have 9 of them, then there's total 9. Let's say that they're connected. Everything is good. So if you look at the calculation, an R is going to be 9, II is going to be 3, OI is going to be 2, RC is going to be 27, RO is going to be 18, RA is going to be 9. Let's introduce a new node, and this new node is going to be a reachable node. So the node is reachable. It has a 3 outgoing, 2 incoming, and would be blocked in the network. So the number of nodes is going to increase to 10 from 9. The number of incoming connections and outgoing connections per node is going to be the same. But RC is the total number of nodes multiplied by the incoming connection is going to be 30. And RO is going to be 10 by 2 is going to be 20. and RA is going to be the difference. It's going to be 10. All right. Now, let's say that the parts, the network becomes the same. Let's say that we introduce a new unreachable node. Unreachable node here comes with a caveat. It does not allow any incoming connections. So the number of nodes is going to be 9 because the unreachable node is not going to be visible, and the I and O is going to be the same, 3 and 2, and RC is going to be 27. You are not adding basically to additional incoming connections. Outgoing connections in the network is going to be 20, and the gap is going to be 7. So you see, the total number of available connections is going to decrease. I apologize for that. So let's continue. Again, remove the node, things will happen the same way. Then the network parameters will get back to the same level. Now, let's systematically do that. Let's introduce a bunch of nodes controlled by the adversary, and those are going to be basically chock the existing network by connected to every available slot. And so RA will be decreased to 0. Now, when a new benign node comes to the network, it will not be able to connect to any of the greens. It's going to be able to connect to only the oranges. And the oranges are those controlled by the adversary, because those are the only one that will pose as reachable, like as ones with available slots to connect with. You connect with them, and then the adversary, as soon as you connect with them, the adversary will go and fill all the slots of the benign blue ones, and thus will not allow anybody to connect to them. And so the adversary will have control over the communication between those and the rest of the world. And so you can imagine this kind of partitioning happen repeatedly. You start with a bunch of nodes that are benign, you partition them into two parts, and then you just refine it. Now, the SyncAttack procedure goes as follows. As default, for incoming and outgoing connections in Bitcoin in particular, you have 115 and 10 nodes, 10 connections respectively. It's not 3 and 2 anymore. And so the total number of connection slots are approximately 1.4 million. And for that, you'll have to purchase a large number of IP addresses. It's going to be very costly. So how to do better? We know that you can run actually multiple connections on a single IP address, and that is thanks to the port idea. So I know it does not distinguish the incoming connections by IP addresses. Rather, it concatenates the IP address with the port. And so we know that there is 65,000 of those port numbers minus the allocated lower range of ports. And those we can utilize, 64,000 of them. And with approximately 110 to 115 reachable nodes with unique IP addresses, the adversary will be able to occupy the incoming connections of all the existing nodes, preventing any connection with them. And so we will be able to realize this idea. And so the way that attack will work is that you will create that kind of competition, those two factions of blue and green. And let's say that the blue had the beta of mining power, the green had an alpha of mining power, and then they will mine over their existing blocks, not being aware of the other part of the network. The adversary will block its own block, its own transaction in competing blocks. And let's say that at any point in time, the adversary will actually plug it in either of them, either of those factions or chains. And what will happen is that at any point in time, there is a chance that alpha will like the group of benign miners with the alpha mining power might win over that of the beta. And as soon as that happens, then the adversary will actually basically propagate the block with the largest, with the longest chain to the other part of the network, and as such, double spending will happen. The adversary will double spend without using mining powers, and the estimated cost is very minor. So, what are the countermeasures for this attack? Well, you can allow only one incoming connection per IP address, and this is going to raise the cost. It's not going to solve the problem. You allow up to 2 incoming connections. Same again, the same issue, but based on measurements of the related nodes, this will increase the attack cost. You refine the eviction logic, evict 1 connection with the longest uptime and 1 with the shortest uptime, and this will affect the reachable and unreachable nodes equally. And so for this attack, it's more of a cat and mouse game. What are some of the open research directions building on that? So, well, Bitcoin is permissionless network. It's evolving, and so looking into that evolution is important. Mapping between overlay topology and the physical topology to understand checking points of this physical network, physical topology is also important. There's also an element of privacy exposure, linking IP addresses, transactions, and so forth. There is also looking into the interdependency between different applications of blockchain systems and the underlying physical network, so that you can look into which part of the network is going to be heavily utilized by multiple applications to optimize attacks. Looking into software vulnerabilities as well, and scalability versus security. So this is the main talk, and I understand I'm doing just right on time to allow enough time for questions. But given that I not have any questions so far, did I have any questions? I'm not sure if I had any questions. The host, did I have any question?
If anyone has any questions, please raise your hand and your mic will be enabled.
Okay, so until that happens, if you have no questions, I have a few more slides that I can go over. Did I? Okay, so let me get back to my slides. So this is only one element of my research agenda. So I've been very fortunate to work with several excellent PhD students who have been pushing for a lot of cool works. And so in the next few slides, I will tell you a little bit about my research statement and approach. And so that if you are really interested in pursuing that, or maybe applying for a PhD in the US, then you might want to consider also our group as potential group that you want to go to. And so a standard thing that we say is the mission, approach, systems that we work on, and school of thought, and then a bunch of applications that we work on. And so the mission of our group is to realize algorithms, protocols, and systems that would be more secure, private, and safe. And for that, we follow experimental approaches at heart and investigate measurement, analysis, and characterization, as well as modeling of the design and use of those systems for better security or privacy. And the systems that we use, blockchain is one of those. I gave a talk today about blockchains, but they are not the only thing, by no means. So we have been working also on IoT, software, AR, VR, social media platforms, machine learning systems, network systems, memory systems, and web systems. And there are 2 pillars of our methods for that, automation and measurement. And so for automation, we use advances in machine learning, representation to create efficiencies, and for measurement, we use evidence rather than theory. And so for the areas that we have looked into, blockchain is what we took today, but we looked also into machine learning and security. We looked into network systems and security, and we looked into software systems and security. And so some of the examples combine actually a lot of those, including malware understanding. And so in our work in malware understanding, we look into detection of those malware, addressing efficiency, and fine-grained understanding. Online safety, we look into the use of large-scale language models, large language models, for something good like understanding improper, inappropriate contents that is targeting kids, for instance, and coping with some issues to deal with in those language models at the same time. For AR, VR, and IoT security, we look into advances in inference capabilities enabled by representation techniques. And we look into new methods that would allow us to cope with those inference capabilities and their application-specific attacks. Another element of work that we have pursued is authorship attribution. And the idea here is to attribute, say, a piece of code to its original author. And in this space, we utilize representation and deep learning capabilities into making attribution practical. And so we also look into designing defenses for those attacks. Finally, we look into also a privacy policy understanding, that is, annotating privacy policies against core, simple to understand components, and understanding inclusiveness in the language policy. So, quick overview of some of the work that we have been doing. We've been looking into identifying features that can be used distinctly to identify malware samples with low cost and fast behavioral identification. We have been looking into understanding the robustness of malware detection engines. That is, look into practical examples that can be evaluated against industrial and research-based detection engines. We've been looking also into building pipelines that can be used for automating the annotation of privacy policies by utilizing large-scale language models. Blockchain, I talk about that in a second. We have been looking into inference attacks and defenses on AR/VR for in-air typing capabilities. We have been looking into generalizable approaches for proactive detection of adversarial images utilizing latent neighborhood graphs and associated detection. We also have been looking into identifying distinctive patterns within malware families that can be used to analyze malware through replay type of attacks. And finally, we have been looking into temporal robustness of malicious code detection over time. This is all I have, so I'll open for questions if you have any questions or whatever you guys want to ask from here.
That was a really, really great job, sir. I had a question regarding, well, the structure of blockchains itself. As in, since we don't have a universally defined protocol for how blockchains should be, so
Right.
that would be a problem in creating new applications of it. What's your opinion on what we could do to tackle this problem?
That's a very good question. I I think there is something that is something there that kind of answer your question. Eventually, we will not be able to have every application speaking the same language and interoperating with every other application out there. But I think with the versatile programming capabilities and platforms that are out there, whether it is Ethereum is more than a single application. Ethereum would allow you to build smart contracts that would serve so many different applications, and those will be able to talk to one another, given that the common aspect between them. So how to back to your question? I guess this is a little bit of mumbling over the answer. Back to your question, how to address that? I think it would come from an intermediary that would make that communication possible. As with the problem is fundamental, and we have addressed that problem in different domains differently, whether it is through serialization, through normalization, standardization, and so forth. And I think there is a chance for doing that as well in those applications. Eventually, not everything is going to speak to everything else, but you can make kind of trends in that.
Thank you so much, sir. Another question that I had is, well, we will be having our final year projects soon. So what would you suggest would be some of the areas in blockchain security that are currently lacking in research, or that could do well with more projects in it or more research in it?
Very nice question. So I think for my view on this is that a senior project, year project is it's a great if it's novel, if it's something that is really new and that is publishable and whatnot. but that should not be the goal. The goal of the senior year project is to look into a real problem and expose the students to it so that the student get the critical thinking skill that can carry forward. And of course, the programming experience, analysis experience, and so forth. So in the blockchain systems in particular, I would look at the existing, in security in particular, I would look at the existing measurement, evidence-based security works from the community and try to reproduce them. And I say that because you heard my talk and you would paint a picture about how the network operates and what are the gaps in it. But some others, based on their analysis, would maybe have a more refined view of it based on the point in time right now, as compared to 2-3 years ago when the study was made. And B, the conditions of the underlying network might change. So this might invalidate, open new directions for attacks, and so forth. This is one. The second one is there are so many applications out there. I mean, I can go back to my initial slide here. If you look here, am I still sharing the slide? Okay. Here, we say that, well, all those applications are security heavy. Mitigating DDoS attacks, verifying software, biometrics private keys, preventing hacks, more secure DNS, and so forth. There is a great opportunity to prototype such applications. And those are all applications for security, like how to realize a more secure DNS that is going to be still providing the same throughput that is desired for DNS. DNS is very scalable, super scalable. The only reason that the internet works today is because of a few stable, despite the incidents that happen every now and then, stable pieces of infrastructure. DNS is one of them. For sure, DNS is the most obvious one of them. If it was not for DNS, you'll not be able to know, how to go to Google, right? Which is maybe the hand and the arm and leg of everyone. So to that end, another direction is by looking into specifying requirements, implementing, and evaluating those various applications that some of them are already existing, some of them are hypothesized. So those are two directions. Other questions? Do we have other questions? Someone, Lutfi, raise hand. Go ahead, Lutfi. I can't hear. Lutfi, unmute yourself and speak. I can't hear anything. Hamza? Ashna? I cannot hear you. Can you raise your voice? Yeah, I can hear it a little bit. Yeah, raise.
There's a question. In your mind, you can ask.
I cannot hear anything.
Sorry, I think there has been some technical issue. Can you hear me, Professor, now?
Yeah, I can. Yeah.
I think, is there anyone who would like to ask a question? I think there is one participant who has opened his mic.
What was the question again?
I think, Hira, would you like to ask something? I think you had your mic open. Okay, I think we have wonderful talks. We are now concluding this session and would like to ask our host Ashna to please deliver the ending remarks.
All right. Well, did I hear that we are concluding the talk, right? Thank you very much.
Yes, yes.
Thank you
Yes,
very much.
Thank you so much, sir.
All right. Take care. Bye. Bye.
I think there has been some issue with our host. I would like to, sir, thank you on behalf of GCU-ACM Student Chapter, Department of Computer Science, and GCU University Lahore for joining us today. It was wonderful talk, and we look forward to have a more wonderful session with you on this topic and on your areas of research. And I think there is one question. One participant has raised his hand to ask the question.
Yeah.
Please enable the mic of the participant so he or she could have the opportunity to ask a question.
Allow mic. Yeah, go ahead. I did.
Okay, thank you, sir.
Go ahead. Lutfi,
Great.
go ahead.
So, yeah, thanks, sir. I'm a PhD student and web developer. I have a question, sir, about the blockchain application. What's the best framework to create an application, blockchain application? Solidity or there is another one?
Yeah, that's a very good question. I can tell you like 10 number of them that are best, but I would not be feeling comfortable advocating one over the other. I think there are so many great options out there, and I think there is a range of boasts out there that compare them, but advocating one over the other would be a liability.
Okay.
All right.
Thanks for your time. Thanks for your response. Yeah?
All right. Okay. Well, thank you very much, everyone, for hosting me today, and good luck with your senior projects. All right. Good luck.
Thank you so much for joining us today. And
all right.
Best wishes for us.
All right. Take care.
Okay, participants, please stay over here. We'll be announcing the link for the EAT certificate. A link will be displayed shortly. Okay, it is displayed. Please type this link on your browser. It will be enabled for only 2 to 3 minutes, so please hurry up, and you will be able to get your EAT certificates. Let me remind you again, this link will be open only for a short while. So please avail this opportunity and type this link on your browser. You will be able to get your EAT certificates. I hope you all have marked your attendance. Now, thank you so much, everyone, for joining us for this talk, and stay tuned to our social media pages for further news about further events of GCU-ACM Student Chapter. Thank you.